So these are the notes for Newton's 3 laws of motion. You need to fill in the guided notes as we go, so feel free to pause this video whenever you need to finish filling in the notes. So the first law says that an object at rest will stay at rest, and an object in motion will stay in motion at a constant velocity unless acted upon by an unbalanced force. So that means it's not going to have acceleration. If it's at rest, it stays at rest. If it's moving at a constant velocity, it will continue to move at a constant velocity unless it's acted on by an unbalanced or an outside force. This is also called the law of inertia. Keep in mind, inertia is not a force. Inertia is not a force. Every object that has mass has inertia. It has this resistance to a change in motion. It does not want to change what it is currently doing. That is inertia. It is not a force. So inertia is the tendency of an object at rest to remain at rest, or if it's moving, to continue moving at a constant velocity. If an object is not moving at rest, it will continue to stay that way until a force acts on it, until, like a book, for example. If a book is sitting on a desk, it's going to just continue to sit on the desk until you go and say, pick the book up or push it or move it. Until a force acts on it, it's just going to keep doing that. So we see this all the time in our daily lives. The tricky part, and the part that's confusing, is that the second part, that an object in motion will stay in motion unless it's acted on by an unbalanced force. So we don't see this in our daily lives here on Earth, because if you push something across the floor, if something's moving, and there's no force pushing it or being applied to it, eventually it will stop. And the force that makes it stop is a frictional force. So friction is going to make it stop. Here on Earth, we have friction. So without friction, like out in space, if you pushed a box or a rock or an asteroid or something like that, it would just keep moving until eventually it hits something out in space. Okay, so it doesn't quite work that way on Earth because we have friction. So friction does eventually make it stop. Without friction, a box would in fact continue to slide across the floor until it hit another object. So Newton's first law and U. So don't let this be you. Wear a seatbelt. So inertia, we can feel that as we're driving in the car. So think about when you're in the car and you hit the brakes, and what do you feel? You should feel a lurch forward. When you hit the brakes, because you're moving in the car is moving, and you're in the car moving as well. When the car brakes, your body wants to keep moving forward. And so that's why you feel that kind of jump forward. And that's also why it's important to wear seatbelts. So because of inertia, objects, including you, resist changes in their motion. When the car going 80 kilometers per hour is stopped by the brick wall, your body is going to continue moving at 80 miles per hour, or 80 kilometers per hour. So that's a little typo there. But that's just a quick little thing about why you should wear your seatbelt and inertia, science. So balanced versus unbalanced forces. So we keep saying unless acted on by an unbalanced force. So the forces, the balanced and unbalanced forces, are all the forces acting on a single object. So there's all kinds of forces acting on an object, and we'll go into all those different forces here in the future. We're just going to kind of leave this as just simple for right now. But there's all kinds of forces. There's gravity. We just talked about friction. There's all other forces out there. So when they're balanced, the forces are balanced. They're canceling each other out. So they're going in opposite directions. Like, for example, one can be going to the left and one can be going to the right. If they're the same magnitude, then they would cancel. If you have balanced forces, the acceleration is 0. But the object could still be moving. So if you don't have an acceleration, you have two things that the object could be doing. It could be moving at a constant velocity. So remember, if you're not increasing your velocity and you're not decreasing your velocity and you're not changing direction, then you have 0 acceleration. So if you have acceleration is 0, you could be moving with a constant velocity, or the object could be at rest. If you have unbalanced forces, so in one direction, one of the forces is greater, then the object is accelerating in the direction of the unbalanced force, and we call that the net force. Okay, the net force is when you cancel out your forces and whatever is left over is the net force. And so that is the direction that the object will accelerate. So the big idea, inertia is the resistance to a change in motion. A net force is always required to change the motion of an object. Inertia is tied to mass. So more massive objects have more inertia. Less massive objects have less inertia. So think about if you are pushing a bowling ball and a basketball. The bowling ball is much heavier. It's going to require more energy to move that the bowling ball compared to the basketball because the bowling ball has more inertia. An object that is moving will continue to stay. That is not moving will continue to stay still until an unbalanced force acts on it. An object that is moving will continue to move at the same speed until an unbalanced force acts on it. Since friction is everywhere on Earth, that is the force that slows and eventually stops all moving objects, at least here on Earth. Newton's second law, this is an equation, F equals ma. So the net force of an object is equal to the mass of an object multiplied by its acceleration. So force equals mass times acceleration. F equals ma. We know that mass is measured in kilograms. Acceleration is meters per second squared. And so when you multiply those two units, you get the units for force, and that is a Newton, obviously named after Isaac Newton. And the abbreviation for that is just a capital N. A side note here, the acceleration due to gravity, if something is in free fall, the acceleration due to gravity is always 9.8 meters per second squared. Okay, so if something is falling or if there's the force of gravity acting on the object, we would always use the acceleration due to gravity, and that's 9.8. And we would substitute a little g into this equation. It would be F equals mg instead of a when we're talking about gravity. So when two objects are falling, and this is kind of trippy for some people, but when two objects are falling, gravity acts on them the same way. So they're both going to accelerate with that acceleration due to gravity, which is 9.8 meters per second squared. But if they have different masses, that means they're going to hit the ground with a different force. They're going to reach the ground at the same time, as long as there's minimal air resistance. As long as there's no air resistance, they will reach the ground at the same time because they have the same acceleration due to gravity. But the force with which they hit the ground is going to be different because to find the force, you do mass times acceleration. And so because they have different masses, they will have different forces. The more massive object will hit the ground with more force. But they will hit the ground at the same time, and we'll watch a video about this in class. Another thing we need to talk about is weight versus mass. So in science, weight and mass are not the same thing. Like in everyday life, you might say, how much you weigh. Well, really, you're describing your mass. Okay, so weight and mass in science are not the same thing like they are, like the terms you might use in your everyday life. So weight is actually a force. And so weight in science, we're going to measure that in newtons. And so that's the measurement of how much gravity is pulling down on you. And then this is how we would calculate the force of gravity, or your weight. So Fg is force due to gravity, and that's going to be your mass times the acceleration due to gravity. Remember, that was 9.8 meters per second squared. So if you know your mass, then you would just multiply that by 9.8, and that would give you the force of gravity, or your weight. And this would change if gravity is different, your weight would be different. So for example, on the moon, gravity is 1/6 that it is here on Earth. And so you would weigh, your weight would be 1/6 what it is here on Earth. So it would be less, actually, because of the different gravitational pulls. So if you theoretically moved around in our solar system to different planets where the gravities are different, your weight would change depending on where you were. Mass, not the same as weight. Mass is measured in kilograms. And this is the amount of matter, the amount of stuff that you have that something contains. And your mass does not change. The mass of an object will not change as you move to different gravitational pulls. So mass is typically probably what you would normally think of as weight. And then weight is mass with the acceleration due to gravity and how gravity affects the mass. That's going to be your force of gravity or the weight. So mass and weight, not the same thing. Newton's third law: for every action, there's an equal but opposite reaction. And so action and reaction forces often get confused for balanced and unbalanced forces. So those are not the same thing. So action-reaction forces always involve two objects that are interacting. So actually in this picture, there are a couple different of interactions here. So you have the foot on the skateboard. So those are two objects that are interacting. The foot is pushing on the skateboard, and this might seem a little counterintuitive, but the skateboard is actually pushing up on the foot. If it didn't push up on the foot, then the foot would go right through the skateboard. Okay, and then also the skateboard is interacting with the ground. So the ground is pushing up on the skateboard, and the skateboard is pushing down on the ground. And there's probably another foot that this person has that pushed down on the ground to get them to move. So that other foot was pushing on the ground, and the ground was pushing back on the foot. That's how action-reaction forces interact. Here's another example. So flying gracefully through the air, birds depend on Newton's third law of motion. As the bird pushes down on the air with their wings, the air is going to push back up on their wings, and that gives them lift. So that's another example of an action-reaction pair. So the bird's wings with the air. If the bird pushes down on the air pushes back up on the wings. In every interaction, there is a pair of forces acting on the two interacting objects. So with balanced and unbalanced forces, those were all the forces acting on one object. With action and reaction forces, we're talking about two objects interacting. So that's the difference here. So imagine a grasshopper on a rock. Okay, so if the grasshopper jumps off of the rock, then the grasshopper pushed down on the rock, and the rock actually pushed back up on the grasshopper. And those two forces, they were equal. They were equal forces, but the tricky part is those two objects have very different masses. The grasshopper and the rock have different masses. So because of the different masses, the acceleration of the two objects is going to be different. The rock is much more massive, it's heavier compared to the grasshopper. And so the rock doesn't move or doesn't move much, and the grasshopper will take off, and it will have a greater acceleration because it has a smaller mass. So acceleration and mass are inversely proportional. That means they're opposite. So if the acceleration, for the acceleration to be very high, the mass would be small. So the smaller the mass, the faster that object will accelerate. And so when you have two forces interacting, the forces are equal, but the accelerations may not be because the objects may have different masses. Okay, so that is the notes. So make sure you have the guided notes filled in and that you submit those. And then you can go ahead and start working on the inertia and mass worksheet that is due tomorrow.